Okay, this is MAC1114 trigonometry. We are in the section concerning angles and their measures, and this is a continuation of that video. We had done examples 1 through 15, or actually 1 through 16 in the last video, and we pick up with linear and angular speed to finish the rest of the examples in this section. So let's begin with the formulas for linear and angular speed. Linear speed is designated by this symbol V. The formula for it is arc length, r times theta, over t. Unless they give you the arc length, then you don't have to plug in r times theta. So just understand that this is arc length, and when needed, you will plug in what it is equivalent to, which is r times theta divided by t. This is the formula for angular speed, which measures the speed of rotation. So be looking for that kind of terminology in the problem as your clue to use this formula. So angular speed is the central angle measured at the center, divided by unit of time. Okay, since the distance traveled along a circle can be given by the arc length, and this is what I just said verbally, that this formula above right here, linear speed, can be written as r times theta, because arc length is equivalent to r times theta, as we just saw in the previous examples that we were doing up here, such as examples 15 and 16, where we were learning about arc length, and we were introduced to the formula for arc length. Well, that arc length is part of this formula. So linear speed can be written like this, as stated, and you can take that theta over t and push it off to the side, pulling the r out front and moving the theta over t off to the side, so that if you want to relate angular and linear speed, that can be done so right here, because theta over t is angular speed, as it says right here. Angular speed is theta over t. So once you rewrite linear speed as r times theta and you pull this theta over t out to the side, you can replace that theta over t with angular speed. So you can actually relate linear and angular speed. Linear speed is angular speed multiplied by r, the radius. Okay, so now let's see some applications of those problems. This is problem number 17. And it says, a water sprinkler sprays over a distance of 30 feet while rotating through an angle of 145 degrees. What area of the lawn receives water? So this is area, when they are asking you for area, that's area of a sector. So that formula is 1/2 r squared theta. In this particular problem, the radius is given as 30 feet. The angle is given as 145 degrees. Please remember that that central angle cannot be used in degrees and has to be converted into radians in order for it to work with this formula. So here is the formula, and right in the midst of using this area formula, I'll also be converting that 145 into radians. So it's 1/2, 0.5, times 30 feet. This 30 feet serves as the radius. The formula goes r squared, and then that central angle, since it is not usable in degree form, I'm going to convert it right out of degrees, as I have in several previous problems. Okay, this will get rid of the degrees and get it into radians. Okay, now get everything calculated. It's 0.5 times 30 squared, the units get squared also, times 145 times pi. All of those are multipliers in the numerator. Only divisor you have here is the 180. Okay, so putting all of that into the calculator, so it's 0.5 times 30 squared times 145 times pi divided by 180. And that turns out to be 1138.83. I'm going to round to the hundredths place. So 1138.83. Again, they're going to tell you whether to round to the tenths, the hundredths, or the thousandths place. I'm deciding to round to the hundredths place. The units are part of your points, so recognize what degree those units are. Anytime you're doing anything involving area, it's units squared, but you can see that in the calculation. Okay, so that's the final answer. That is the area of this sector with this central angle of 145, but converted into radians and a radius of 30 feet. And example 18. This talks about the windshield of a car and how this arm has a total length of 10 inches that rotates back and forth through an angle of 91 degrees. What is the area of the portion of the windshield that it's cleaned by the 7 inches of this total 10 inches? So basically in this problem, the only thing that's getting wiped out is this. So what you could do is you could do the area of this entire sector from the top to the bottom using this 10-inch as the radius, and then you could take out the 3 inches that's up at the top, what would be wiped out with that, leaving you with just the portion of the window that gets wiped by the 7-inch blade. So I'm going to do this in parts. I'm going to do the area swiped out by the 10-inch blade. So I'm doing all of this area from top to bottom. Okay, again using the formula, area of a sector. Remembering that that 91-inch central angle cannot be used in degree form, so this will be 0.5. Right now I'm doing the area of the sector imposed by that 10-inch total arm. So 10 inches I'll put for the radius. I'll square it like the formula says. And then my theta, instead of using it in degree form, I'm going to convert it out of degree form right in the midst of doing the area of the sector for the 10-inch total arm. Okay, so this will be 180. I'm getting rid of the degrees, bringing it into pi form, or in other words, radian form. Get my answer for that. 0.5 times 10 squared times 91 times pi. That's everything in the top, and then finally divided by 180. And that gives me, oh, something went wrong there. Let me try it again. 0.5 times 10 squared times 91 times second function pi divided by 180. And that gives me 79.4 inches squared. And then let's talk about what gets swiped out by just 3 inches, which is the top. That's not really what's being covered by this 7-inch blade. We want to know just what gets the area that gets wiped by this 7-inch blade. So I'm going to take off the 3 inches at the top. But first I want to figure out the area wiped by the top 3 inches, which is really not being impacted by this 7-inch blade. So it would be 1/2 r squared times theta, which is 0.5. I'm using 3 inches this time, squaring like the formula says, using that same central angle, but converting it into radians. So those would go away, just like I got them to go away here. We're going to put all of this in the calculator. 0.5 times 3 squared times 91 times pi divided by 180. So it's going to be 0.5 times 3 squared times the 91 times the pi divided by 180, and that is 7.1 inches squared. So that inches squared comes from this piece right here. And then if I want to know what is the area cleaned by the 7-inch blade, then I need to work these two answers together. I need to consider the area that is cleaned by the total 10-inch arm, which was 79.4. Take off the area that is the area of the sector impacted by the top of this 10-inch pole, which is 3 inches, so that I'm only left with 7 inches. So the area cleaned by this arm right here is 7.1 inches squared, and I should keep the units on there. So the total area that is cleaned by just the lower 7 inches of this 10-inch arm would be, this minus this would be 72.3 inches squared. And that's your final answer for the 7 inches of that total blade arm. Okay, moving to number 19. This says an object traveling around a circle with a radius of 12 centimeters. An object is traveling around a circle with a radius of 12 centimeters. If in 20 seconds a central angle of 1/3 radian, so there's your central angle, is swept out, what is the linear and angular speeds of the object? Okay, so you have a circle, there's an object traveling around the circle. They're telling you circle has a radius of 12 centimeters, and in 20 seconds, a central angle of 1/3 radian is swept out. So what is the linear speed? For linear speed, we're using this formula right here. Let me get a better writing instrument here. Okay, linear speed, this is the formula. It is S, arc length, divided by T. Arc length is the same thing as R times theta, which the only reason I'm rewriting arc length is because I need to drag a radius into the problem, which we have right here, and central angle. And by replacing arc length with its definition, I drag those two pieces of information into the problem, which are being given for us to plug in. Okay, so the radius here is 12 centimeters. I just plugged in for that. The central angle, which is what theta is in all of these problems, whether you're doing arc length, whether you're doing area of a sector, or whether you're doing linear or angular speed, that theta stands for the central angle, has to be in radians, which it is. They've given it to us in radians, so that's just 1/3 of a radian, and you don't have to write that unit unless it's the only unit in the problem, then you can keep it in there. And then the amount of time that all of this is happening in is in 20 seconds. So V turns out to be 12 times 1/3 is the same thing as 12 divided by 3. That would be 4 centimeters at the top, 20 seconds at the bottom. So this ends up being, if you reduce this fraction, 1/5 centimeters per second. See, and so that would be that answer right there, and you can just put them there if you want, but you may have to fill it in like this separately depending on the software that you're using to do your homework. Okay, angular speed. So angular speed has a different formula. For angular speed, it is the central angle that is swept out per unit of time. So the central angle that is swept out in this particular problem is 1/3 of a radian. Now here, notice that at the top I had centimeters and radians. If there are any units other than radians, go with just that unit and you don't need the radians. However, if radians are the only unit that's around, then you can keep that in the answer. If it's the only unit that's in the numerator. Unit of time was 20 seconds. So this is 1/3 divided by 20 seconds, which is the same thing as instead of dividing by 20, multiply by 1/20. We have radians in the top, so this is 1 times 1 is 1, bottom times bottom is 60 radians per second. So 1/60, and if they're only giving you one spot to give your whole answer, then you can give the number and the units right then and there. That's typically the way it is. It's just that this is separated out. And then to give this second answer, that would be just radians per second. Okay, so both linear and angular speed for the given information. Moving to number 20. In problem number 20, it says a gondola on an amusement park ride spins at a speed of 15 revolutions per minute if the gondola is 23 feet from the ride's center. So with that information, they're describing a radius. I mean, if I try to draw this, I don't know how good this is going to be, but it's like this is the arm of the gondola, and then the gondola where people sit. It's 23 from the ride's center. So what they're really giving you there is the radius. Okay, so in this particular problem, let's see, what is the linear speed of the gondola in miles per hour? So first of all, it says it's spinning at a speed of 15 revolutions per minute. 15 revolutions per minute. Okay, and then as you were going over in previous pages, like on the very first or second page, I believe we went into what a revolution is. One full revolution is 360 degrees, full spin around a circle, which is equivalent to 2 pi. You want to be working in radians for this problem. So 15 revolutions, if one revolution is 2 pi, then this is 15 revolutions, each one worth 2 pi. So this would be 30 pi per minute. Okay, let's see, this is spinning 15 revolutions per minute. That's the same thing as spinning 30 pi, a distance of 30 pi per minute. And then we were asked to give what is the linear speed in this problem. So linear speed formula is S divided by T, which is arc length divided by unit of time. And so arc length is the same thing as R times theta divided by time. And in this particular problem, the R is 23 feet. And the speed at which it's spinning was given in revolutions per minute. I converted that into radians per unit of time. So 30 pi per minute, which I did right up here. Okay, so this would be equal to, just multiply 23 times 30 times pi, and that would be 2,167.7, keeping it to one decimal place, 0.7 feet. That's the unit up here per minute. Okay, however, in this problem, I believe somewhere in here they ask you to give the linear speed, which we have just found. They ask you to give it in miles per hour. So the last thing you want to do is comply with this request to convert it into miles per hour. Right now we have the linear speed. We do have the linear speed, but right now we're in feet per minute. So let's just take that answer. 2,167.7 feet per minute, and we're going to convert into the requested miles per hour. Okay, so there are 5,200, I'm trying to make feet go away, just converting from feet to miles in 1 mile. 1 mile is equivalent. Whenever you're using a conversion fraction, you're trying to make one unit go away and go into the requested unit. And the things that go into the fraction are things that are equal to each other. 1 mile is equal to 5,280 feet. So right now I'm in miles per minute, but they want miles per hour, so I also need to make these minutes go away. So I'll do another conversion here. I want minutes to go away. Units only go away when they're on opposite levels. In other words, that unit is in the numerator and the denominator. I want minutes to go away, so I'm going to put minutes up here. I want to bring hours into it, and the equivalency between these two is that there's 60 minutes is equivalent to 1 hour. Okay, so now I have the unit minutes gone, and I'm left with just the units that they've asked me to give my final answer in. Miles up here is the only unit left now, and hours is the only unit left here. I just need to get all these numbers into the calculator. Anything that's at the top is your numerator. They are all multiplied, the numbers that are at the top, and then these numbers that are in the bottom are the divisors. So it's 2167. 2167.7 times 60 is this, divided by, your only divisor is 5,280. So divide by that, and you end up with 24.6 if we round to one decimal place. And report those units that you just converted to. Okay, so this is the final answer. So obviously problems are getting harder as you get to the end. This is the last problem, last application problem in this section. And in number 21, okay, let's see. It talks about, at a museum, you can see the 4 cable lines that are used to pull cable cars up and down a hill. Each cable travels at a speed of 9.6 miles per hour. Now that is linear speed. Okay, and I know that this is linear speed, which is the same thing as V in those formulas that we've been using, this V right here, because when they talk about angular speed, they'll talk about it being a certain rotation. It'll be related to the rotational speed. Okay, this linear speed is caused by a rotating wheel whose diameter is 9.5 feet. How fast is the wheel rotating? So when they ask you, how fast is the wheel rotating, that means they use, whenever they relate it to a rotational speed, they're talking about angular speed, which is that omega symbol. Okay, now there's a formula that relates angular and linear speed, which I spoke about when I started this second video, and that was right here. Let's see if we can pull those up. Okay, that linear and angular speed are related by this equation, and we went through the substitutions that led up to this. Linear speed is equal to the radius times the angular speed, which is what we're going to use in this problem. Okay, so linear is equal to the radius times angular speed. Okay, so I believe you were given a linear speed of 9.65 miles per hour, but then the radius, which is going to be half of this, the radius is going to be this 9.5 feet divided by 2, because that's the diameter. We're not using diameter in this formula, we use radius. So the radius is 4.75 feet, but these are not compatible. You're going to plug in something here that's in miles per hour, and then you're going to be using something over here that's in feet. So you need to make these units compatible. So what we're going to do here is turn this 9.65 miles per hour into so many feet per hour so that you have the same kind of length unit on both sides. As I said, we're going to be plugging this in, it's in feet, yet this one's in miles. So to make them compatible, I'm going to take that linear speed that they've given us, which is this value right here, and convert it into feet first. So this is going to be my first step. I will be coming back to this formula because in the end, I want to know how fast is the wheel rotating, which is omega. So eventually I want to solve for that omega, but right now I'm worried about the units not being compatible. So first thing that I'm going to do is I'm going to take the linear speed, this v of 9.65 miles per hour, and I'm going to convert it into feet. And actually, what else is here? How fast is the wheel rotating? Okay, this also, I noticed that when they asked the question here, how fast is the wheel rotating, express your answer in revolutions per minute. So we want the unit of time to be in minutes. Lots of things to worry about here. And the revolutions, that can easily be brought in at the end. But I know as far as getting the units compatible and getting them in a way that I can report the answer the way that they have requested, I first want to get the units on this side and this side compatible, and I want to be reporting my unit of time in minutes. So a few things to tackle here. Okay, so 9.65 miles per hour. I'm going to get out of miles, so 1 mile is equal to 5, and get into feet, just like the radius is in feet, 5,280 feet. Okay, I also, as I stated, they want the unit of time to be minutes in the final answer, so how about we get out of hours and go into minutes? So here, let's convert again. Let's get rid of hours. 1 hour is equal to 60 minutes, and drag minutes into the problem. Okay, so if I multiply all these things and then use my divisor here of 60, it would be 9.65 times 5280 at the top, and then divided by 60, which gives me 849.2. And let's report the units that remain at this point. We have feet left, we have minutes left, so feet per minute. Okay, so now instead of using 9.65 miles per hour in here for V, we can use something that's compatible with a radius that's also in feet. We can use 849.2 feet per minute instead of 965 miles per hour. Okay, so in the next step, I'm going to come back to this formula. Okay, realizing that I want to solve for omega. How fast is the wheel rotating? So I can manipulate this equation if I want to isolate omega as I do. And I can do it right now, or I can just do it in the midst of solving. So I think I'm going to do it right now. I'm going to just divide by R, and get an expression for omega, which would just be V over R. If you divide by R here and divide by R here, you have this expression. So this is what I'm going to be plugging into. Okay, so my omega is equal to my angular speed is equal to the linear speed, but now that I've converted it into units that are compatible with the rest of the quantities in the problem, I can use linear speed, 849.2 feet per minute, divided by the radius, which is 4.75 feet. Those feet would cancel. These minutes are going to stay in a denominator when I report them. So I'm going to go 849.2 divided by 4.75, which is 178.8. Minutes are part of a denominator. And then, the final request is that I should be reporting my answer in revolutions per minute. Right now I have it I know that it's 178.8 per minute, but if I want to relate that to revolutions per minute, then I can just drag that in right now. Okay, my angular speed is 178 per minute. 178.8 per minute. And I can drag in, I want to have an answer that's revolutions at the top, minutes at the bottom. So I can go multiply by 1. Revolution is equivalent to 2 pi. So I can drag revolutions into this problem. So this will be 178.8 times 1. 178.8 with a unit of revolutions at the top. And then at the bottom, the only unit that's there is minutes. And 2 pi is down here. Now let's consolidate these numbers. We're going to put in our calculator. So instead of having 2 numbers as a coefficient, we'll just have 1 number. 178.8 divided by 2 pi. I'm going to let it multiply the 2 and the pi first and then divide by that, which is 28.45. This one says round to 2 decimal places, so 28.45. The unit of revolutions per minute, and that is our final answer for that problem. That completes all the problems for the section on angles and their measures.